So this is EE698G, lecture 5. So our main aim is to understand a circuit called as delay lock loop. So this consists of a reference signal, which is usually a clock that is being given to a VCDL, that is a voltage controlled delay line. Then we take the output of the VCDL and we compare an output edge from the VCDL to the next edge in the clock signal. What block do we use for this? So we use a phase detector to measure the phase between these two signals. Following this, we have a charge pump. And then a capacitor. So under steady state conditions, we know that voltage will develop across this charge pump. And this voltage will be such that the delay of the VCDL under steady state condition will be equal to 1 clock period. So initially, we spent some time trying to understand how a VCDL can be implemented. We saw that two ways to tune the delay is to either tune the capacitance or you tune the charging discharging currents. So you tune one of them and you can achieve a tunable delay. Now we are focusing our attention on the phase detector, right? And what is the first phase detector that we saw? We saw a multiplier-based PD. The concept was very simple. You have in1 and you have in2. Multiply both of them, you get an output signal VPD. Do you relate VPD to phase error? We relate VPD average to phase error, right? And once you do this, what is the output signal you got? VPD average is? So assume in1 was some A1. So you can refer to your notes. The signal VPD average you got was A1, A2 by 2 cos of phi error, right? Then we saw the definition for the gain of the phase detector, which we represented using KPD. What was the definition? That is derivative of the VPD average with respect to phi error. This is also same as the slope of the VPD average versus phi error curve. Okay, so quickly, please sketch VPD average and KPD for a multiplier-based PD. So VPD average versus phase error, we have already plotted. Right, what did you get? Yeah, it was a cosine signal. What comments can you make about KPD for this? What is the exact expression? You have VPD average here. Minus A1, A2 by 2 to sine of phi error. Right? So this was phase error here, VPD average here. Now we can also sketch KPD versus phi error. Then it will look like an inverted sine wave. Does this make sense? Have I plotted it correctly? I have to mark the pi by 2 here. Does this make sense to you? Now, we mentioned that the natural locking point for this is at what phase error? That was at pi by 2. And we see that the magnitude of the gain is maximum at pi by 2. Right? The slope is maximum at pi by 2. Now, that is generally a good thing because it means that closer to the locking point, you are more sensitive to variations, which means if you vary from the locking point, you will come back to the correct point immediately. Right? Okay. So we have now seen the multiplier-based PD. Do you remember the next PD that we were supposed to look at? Yeah.
What is the intuition behind locking point being pi by 2?
Intuition behind locking point being pi by 2. So it is a little tricky to answer now completely because we don't know the full system yet. We are working with a very crude form of a DLL, right? But let me give you in general terms. So any feedback system will usually compare something, take a difference, and will try to minimize this difference, right? And then you have some processing circuit.
You try to drive that error to 0.
It will try to make this error to 0, right? And this processing is done based on something that is sensing it, and then some more processing on it. Then based on that, you go and tweak some parameter. This is what we have also used now, right? Now, if the sensing element is giving you 0 at some instant, right? Whatever the sensing element is sensing as, that is what it is trying to reduce to 0, right? So the sensing element is giving you 0 here. Sensing element is giving you 0 corresponding to phase error of pi by 2. What that means is the rest of the systems are processing a 0, which means corresponding to that, it is not going to make any change.
The output is delayed by t clock.
The output is going to be t clock by 4, right? T clock is 2 pi, t clock by 2 is pi, t clock by 4 is pi by 2. So I'll take 2 square waves. Right? Now the phase difference between them is 0. Okay. Let's say I delay the second signal to so much. So this is in 1, this is in 2. My delta t is so much. So my phase error is 2 pi by t naught into delta t. Right? So this is basically 2 pi into delta t by t naught. I think this expression is sufficient to answer your question, right? So if delta t is t naught, phi error is 2 pi. Right? If delta t is t naught by 2, phi error is pi. Right? That is one way to look at it. Or a quicker way might be, let's say I have 2 sine waves. Right? When you say this is 2 pi for you, right? 2 pi radians to get one full period. Pi radians to get half period. Pi by 2 radians to get 1/4 of the period. Now, the reason why I said it is a little difficult to answer now is we don't know exactly how the rest of the modules are configured. But roughly, if the initial sensing element is giving you 0, then the rest of the elements are not going to process much on it. Right? So you are sensing something. Yeah, you are sensing something and trying to make that 0. So wherever the sensing element is giving you 0, this will be your locking point. That is when the loop will achieve steady state. Now, once we start putting everything in loop, then these concepts will become much clearer. Okay, so the next phase detector that we want to consider is a sample and hold based PD. The idea is very simple. You sample one input using the edges of the other, and you hold the value till it is time to take the next sample. And this particular phase detector is used when you have one of the inputs as a sinusoid and the second input as a square wave. In this case, it's especially easier to use this PD. So now let me start with in2 being delayed by some small amount. So all that we are going to do is at the rising edges of in2, I will sample in1. So these are the samples you get, and you sample and hold that value, right? Now, even before we get to the full-blown mathematical analysis of this, can you tell me what is the behavior you expect? Roughly, when you will expect to see the maximum, minimum, etc. So if I'm looking at VPD average versus phase error, where do you think you'll get 0?
Okay.
So for example, in this case, in this particular scenario, your VPD is you have obtained a sample value here, and then you hold it till the next sample, which is here. Then you hold it till the next sample, which is here. So if your phase error is constant, you basically have a DC value, right? When do you think this DC will be equal to 0? How should I position my into? So imagine moving your into to the left and right. How should I position my into such that VPD is going to give me 0?
Delta T is 0.
Delta T is 0, right? For this particular scenario, you have to sample these points, right? Where will you get the maximum?
Pi by 2.
At pi by 2. Minimum?
Pi.
Pi is again
0.
0.
Minus 3 by 2. And 3 by 2.
Either 3 pi by 2 or minus pi by 2. So that is the intuition we have. Now let's try and model this and see if the results are matching the intuition. So to model this, let me call my in1 as sine omega naught t. Right? Let me call my in2 as some gamma of omega naught t minus, what is the expression? Omega naught into delta t. Now my VPD is basically samples of in1 at t equal to, can you give me a generalized expression? What is this instant? T equal to delta t. This instant? So if I call my period as t naught, this is some period plus delta t. And this is twice t naught plus delta t, right? So I can generalize this and say this is equal to n times t naught plus delta t. Okay. So now I simply have to put this in the equation for in1, which is sine of omega naught into n times t naught plus delta t. So this is sine of n times omega naught t naught plus omega naught into delta t. Now I can replace omega naught with 2 pi by t naught. Then these two will cancel. And I simply have 2n pi. What about this term? That is phase error, right? Your into was lagging in1 by delta t, in which case your phase error would have been omega naught into delta t. So this is now your phase error. And I can simplify this expression as sign of phase error. Okay. So quickly calculate the KPD and plot VPD versus pi error. Yeah, so this expression is for VPD. What would be VPD average? Same. This is not time varying, it's a constant. What is your KPD? Cause of phase error. Okay. So can you identify a monotonic range for this? So the curve is monotonic from minus pi by 2 to plus pi by 2. And this gives you a range of pi. Is it linear in this range? No, it is non-linear. So any questions on this sample and hold PD? So did our intuition work out correct finally? Okay. So next we move on to the digital PDs. What would be the locking point? 0. If you use it as it is, we would expect the locking point to be 0. But this is again something that you will have to put it in the loop and then verify. But the default locking point, we would expect it to be 0. Right. So we move on to the digital phase detectors. Now the reason why they are called as digital is because the input waveforms are more digital looking in nature. They go from 0 to VDD instead of with a sine wave. Also, most of these digital phase detectors will have logic gates being used for their implementation. So the first logic gate we'll deal with is an XOR-based PD. Okay. So let's say I have in1 and in2. These are fed as inputs to an XOR gate. Let's say the XOR gate has supply as VDD and ground, so that the output waveforms are swinging between 0 and VDD. And this is your output VPD. Quickly, let us look at the truth table for XOR. 0, 0, 0, 1, 1, 0, 1, 1, 0. Good. So now let me give you a problem to solve. I'm giving you a in1 and in2 waveform. So in2 is delayed. And this delay is by some delta t. Right? You have to plot VPD and then calculate VPD average. Why don't you try this? You can assume that the period is T0. So let us sketch VPD. So it's 0 here. It becomes 1. What is the width of this region? This is delta T wide. Then it goes to 0. Then it goes 1 again. Again, width of this region. This is also delta T. Then 0. And then this portion is periodic now. So it repeats, right? What is the period of VPD now? It is periodic with T0 by 2. This is assuming 50% duty cycle for N1 and N2, right? So now to calculate VPD average, what do I have to do?
T0 by 2 will be
Till the, yeah, right. So to calculate this, I simply have to look at the area under the curve and divided by the time period of observation. So this is VDD for delta T duration divided by T0 by 2. So let me take VDD by 2 to one side. What can I write delta T by T0 as? So
it should be 2 VDD.
All right, 2 VDD. So phi error was equal to 2 pi by T0 into delta T. Right? So I can, wherever I see delta T by T0, I can simply take 2 pi to this side and replace it as phi error by 2 pi. So I replace this. And this is equal to phi error by 2 pi. So this gives you pi error into VDD by pi. Okay. So this seems to suggest that as your phase error is increasing, your VPD average is also going to increase linearly, right? Now, we want to know if this is true for all values of phase error or if there is a range for which this equation is valid. So to point you into that right direction, I'm going to give you 3 cases. You can sketch for all 3 and see if this, see how we can get VPD average versus phi error plot. So you have to you have to calculate VPD average for phi error equal to pi, for phi error greater than, so phi error between pi and 2 pi. And you also do this operation for phi error between minus pi to 0. So you will have to adjust your into for all 3 conditions and see if you are still coming up with the same result.
It is calculated from
minus pi to 0. So what we are looking for is a plot of VPD average versus phase error. I want to see what the result will be from minus 2 pi to plus 2 pi. So far you have got the result that it is going to be equal to VDD by pi into phase error. So for what range do you think that result is valid? 0 to pi. Okay. Is that clear? So imagine pulling this into signal to this side, right? If the width of these pulses are increasing proportionally, right, then you know that this relationship is valid, right?
Even minus pi to 0.
Minus pi to 0.
Sure.
Does it work? So imagine the signal is being pulled to this side, right? Where does it hit the maximum? Is that clear for everyone? Because when the signal reaches here, yeah, so if this was in 1, and if your in2 was here, then VPD is simply VDD all the time, right? So I can confidently plot this till pi. What happens after pi? It decreases, right? And it will decrease in a linear fashion. So it will come back to 2 pi. How should it look on the other side? Similar, right? You don't have negative values, so it is expected to look like this. Is this okay? So I'm sure this part everyone is confident about, right? No confusions on this line, right? The rest again, you can sketch the waveforms, right? Go back and sketch the waveforms and you'll see that it follows a similar pattern. Okay. Now tell me, where should the locking point be? At 0. So do you think this is a good locking point? Why?
Okay. Can we
So we are now at the edge of 2 monotonic regions, right? If you log there and there was some small signal noise or a small signal, you might shift to either of the sides. But you would have configured your loop to work for one of the KPDs, either for a positive KPD or for a negative KPD. So this is clearly a dangerous locking point for us, right? So what we would generally do is, we would process this waveform slightly such that the curve shifts downwards. So you would try and achieve a shape like this, where this is at pi, this is at pi by 2, and this is 0. So would basically downshift the curve, and you don't have to worry about how we'll do it. It is possible to do it either by modifying the XOR slightly or doing some processing immediately after. But it is important to recognize that this characteristics of VPD average versus phi error is not what we will use eventually. We will require a characteristic that looks like this. Then you would shift lock to pi by 2, right? You would lock at the center of a monotonic range. So now so anytime we talk about XOR, it is with the understanding that the curve has been shifted such that the locking is happening at the center of the monotonic region. So now the monotonic range is from where is the range? This is from 0 to pi. Or you can choose from minus pi to 0 also, right? And this gives you a range of pi. Is it linear or non-linear? It is linear within this monotonic range. Now that is very interesting, right? Is XOR linear or non-linear? So you have a very non-linear element, a logic gate. Even when you change your VIN, the output is either going to be 0 or 1. The output is not increasing proportional to the input. You have taken a non-linear element, and because of the way how we have defined our relationship, we now have a very linear relationship out of it. Can you also sketch the KPD versus phi error plot? How do we shift it down, right? So again, let us look at the full loop and then we can come back to these questions. Right. That is one way. If you have your XOR power supplies from minus VDD to plus VDD, this is possible. Now, there are other things you can do even if minus VDD supply is not available. But those questions are better answered after we know the loop completely. So how does your KPD look like? What is the value? This is equal to VDD by pi. Here? Minus VDD by pi. So if you look at your KPD versus phase error, this will be VDD by pi till what value? Till pi. And then it will shift down to minus VDD by pi. Same on this side also. You'll have minus VDD by pi. And then after that, VDD by pi. Okay, so let me give you a few questions to try out as homework. So plot VPD average versus phi error when in 1 and in 2 have pulse width equal to T0 by 4 for the XOR-based PD. Right now, we have considered a 50% duty cycle, which meant that the pulse width was T0 by 2. So now both the signals have a smaller pulse width. Repeat the same procedure. Plot the timing waveforms, calculate the average VPD, and then imagine how this, the timing behavior is going to change if you move into to either of the sides. So that will tell you where the limits of the equation you derived are. Now the second question is, let's say I have an XOR-based PD. Now, instead of directly giving the input here, I give it to a divide by 2 stage. And my input is given here. Yeah, duty cycle is different. Duty cycle is at 25%. Okay. Now, third question. So this is the point that he raised. You have to plot VPD average versus phi error for the XOR PD when the supply is from minus VDD to plus VDD. So instead of going from 0 to VDD, your output signal is going to switch from minus VDD to plus VDD. So you have to calculate the average and then plot the wave. Now, one question for you to try out right now. Now, let us assume that in1 has a pulse width, which is T0 by 2. In2 has a pulse width, which is lesser than T0 by 2. That is, the duty cycle is smaller than 50%. Can you figure out how your VPD average versus phi error plot is going to change? So the steps to do are similar. You start with in1, a waveform for in1, a waveform for in2, where the pulse width is smaller than 50, duty cycle is smaller than 50%, sketch VPD. And then see how the shape is expected to change. A qualitative answer is sufficient. Okay, let's see what we'll get for this case. So I've considered an N1 and an N2. The N2 has a smaller pulse width than N1. So let us start with the point where delta T is equal to 0. So the rising edges of N1 and N2 are exactly aligned, right? So the output I get, so it is 0 all throughout, and I'll get a small pulse here. And then it is 0 all throughout, and I get a pulse here, right? So what is my output signal periodic with now? What is the period? T naught, same as the periods of N1 and N2. So that is one difference that we notice immediately. Now let's say I shift my N2 to the left side by a small amount. So my N2 is now like this. Right? Now corresponding to this, I will have a pulse here. And this pulse is now going to be smaller. Right? So first of all, for delta T equal to 0, we have a non-zero average. VPD average is a finite value. Now, when delta T is increasing, I get a slightly different waveform. Now, I'm interested in checking if the new average has increased or decreased. What do you think? It has remained the same, right? So what is happening is, if the area of the earlier pulse was so much, now you see that the area of these two pulses will be same as that. Whatever is the width of this pulse, your original pulse has decreased by the same amount, right? And up to what point will this continue? Till your edge, till this falling edge begins to appear here, right? Till that point, it will be constant. So effectively, in the original plot, now at t equal to 0, I start with a finite value. It remains constant. And then it will simply follow the curve. So then it will reach here, and then it will again be constant for some more time. And then it will come down after this, etc. So this is the new shape of the curve. How does your KPD change? So KPD is now 0 for this duration. Right? Is that a problem? The properly monotonic region decreases, but at least it is not becoming negative value. So that actually depends on how the loop is constructed, right? But it is something interesting to note that KPD is 0 here. So if you had a small signal, the gain of that small signal is going to be 0, right? So how this is going to function? Sorry. If there is small signal change around the bias point, that small signal change is not going to respond. But so again, let us construct the loop completely. So this is something to keep in mind. We'll analyze what happens if this model is present once we know the loop. Okay. So any other questions on this? So the same method that we use for analysis right now, you can analyze all the other examples I've given using the same approach. So now we move on to an SR latch-based PD. So let me refresh your memory on the SR latch. Let's implement a NOR to base latch. This is reset R. This is your set input S, Q, and Q bar. So let's quickly start by sketching out the truth table for NOR. How does it look like? 0, 0 for NOR 2. 0, 1. So what this quickly tells you is if one of the inputs of the NOR is a 1, you don't have to worry about what the other input is. You can directly put it as 0. Right? If one of the inputs is 1, directly put it as 0. It doesn't matter what the other input is. Okay. Now, based on this, can you quickly write the SR latch table? A truth table for SR latch. So what we are looking for is SR, Q and Q bar. Let's look at this scenario. S is 0 and R is 1. What should be Q? So because R is 1, you know Q is immediately 0. Right? So now if Q is 0, this is 0, S is also 0, therefore Q bar is 1. So this gives you 0, 1. For 1, 0, 1, 0. For 1, 1, but what would be the output? Why is it not defined? Okay, so I will not call this as Q and Q bar. Then is the problem solved?
No, we don't know it will go to 0 and
Why? So I'm going to call this as output 1 and output 2. Let's check if this is a stable situation, right? So now my reset is 1 and my reset is 1, set is 1. Because reset is 1, I can directly say this is 0. Because set is 1, this is also 0. Is it consistent? It's consistent. So this is equal to 0 and 0. Right? Now, when S and R are 0, 0, it is going to hold the previous state. So for example, let's say if both of them were 0, 0, if both of them are 0, 0, now whether the output is 1 or 0 depends on, now whether the this output is going to be 1 or 0 depends on this, which depends on this value. So now originally if this was 1, then you have 1 and 0, this goes to 0, and this is at 0, right? So then you have a consistent solution. If you assume the opposite outputs, then that also will result in a consistent solution. So whatever was the previous output, it is going to hold that state. Okay. Now you mentioned that this is a forbidden state. Why? Because looks like we have a very consistent solution here, right?
You can't come out of that to 0, 0.
Correct. Right. So as such, this state doesn't have a problem. One reason why people call this as forbidden state is, one, when you use it in memory and you are dealing with the outputs as Q and Q bar, then Q and Q bar do not follow that relationship. That could be one reason. The other reason is, let's say you are going from the 1 1 output to the 0 0 output. So now there are two ways in which you can do this, right? So your S and R have to eventually get to 0 0. It's possible that on the way it went like 1 0 and then 0 0, or it went to 0 1 and then 0 0. Now both these transitions are going to result in entirely different outputs. If you followed the first path to reach here, what would be the output? This will result in an output of 1 0. If you followed this path, you will get an output. You will get an output of 0 1. Now, if the edges were happening very close to each other, sometimes it is not even a function of which edge has occurred. It could become a function of the noise in the system. In the presence of the noise, in the presence of mismatches between the set and the reset paths, even if the reset occurred before the set, it's possible that because of some noise or mismatch, especially if it has occurred very closely, your SR latch might detect it the other way, right? So then the output path that you will get will depend on the noise also in the system, which is something you want to avoid if you're working with memories. So you try and avoid this state altogether. That's all. Okay. But other than that, this is fine. You don't have any other issues. Is this clear? Now we have an SR latch. Can you sketch an N1 into sketch VPD and find out VPD average versus phase error relationship? What is the first problem you are facing? No. Yeah. What is your VPD now? You have two outputs, right? You don't know what to call as your VPD. So let me give you, let's say this is corresponding to reset. You can call your signal as up. Let's say I call this signal as up. And this signal as down, right? And then you give your in1 to the set and in2 to reset. So you have in1, which is your set signal, as some input like this. In the reset pin, you will give into, let's say this is a delayed signal. Now you have your up, which was originally your Q. Then you plot a down, which was originally your Q bar. And based on this, can you tell me whether the information is present in the up signal or in the down signal? Information is present in the up signal. Okay, let us sketch it. What comment can I make about the plot before this? Both in1 and in2 are at 0. So it is holding some previous value. I don't know what the previous value is, so we'll not worry about it right now. Right? So here S is 1 and R is 0, which means your up is high. Then both of them are 1, which means it will come down. And then S is 0, R is 1. So it remains at 0. Both of them are 0. It holds the state. Then it goes high again. Now at this point, I have completed one period. So I can confidently sketch the same waveform throughout. Right? Now for down, how would down look like? Can I directly, invert up and sketch it there? No. So here it is 0. When both of them go high, it remains at 0. Now it goes high here. And it remains high till this point. And then this is now periodic, so I can directly sketch the next waveform here. This is okay? So tell me the width of both the pulses. What is this width? This is delta t. What about this? This is whatever is the time period divided by 2. Okay. Now it looks like the information we want is in up signal. Right? It looks like we should define our VPD as up. So I'm going Where does the up go high? So S is 0, R is 1. Therefore, up remains at 0. This was equivalent of our Q. Then both of them are 1 now. Therefore, up still remains at 0. Now you have 1, 0, which means up goes high. Now both of them are 0, so it holds the state. Now we have completed one period. So I can simply repeat the waveform. Now we look at the down signal. Now here S is 0 and R is 1, which means your down is high. Then both of them are 1. So it comes down. What happens here? So S is 1, R is 0. Therefore, it remains. And then 0, 0, it holds. Okay? And then I can repeat the waveform. So now the information delta t is present in the second signal. Whereas the up signal has a constant width of T0 by 2, where this was my delta t. So what do we do now?
Addition.
Why addition?
Addition is constant for both the cases.
So what do you mean by addition? What two signals are we adding?
Up and down.
Okay, we add up and down. then
the average will be like delta t plus t naught by 2 always.
So this is a very good suggestion, right? What he's saying is instead of relying on only up or only down, and why can't we just rely on up and down? Because once it is fabricated, the phase detector is supposed to tell us whether the phase is a positive value or a negative value. So clearly, we have to use some linear combination of up and down. So the suggestion you are giving is to add them, right? This is in the right direction. But this suggestion where we add up and down, can it differentiate between positive delta t's and negative delta t's? Whether in-one is lagging or leading into, can it differentiate?
After taking average,
we won't be able to tell, right? So what other linear combination can you think of which will bring out this information about which signal is leading and which signal is lagging? Is the problem statement clear? Is it clear? Okay. So addition is out. What is the next thing that you'll think of? Subtraction, right? So instead of using addition, we'll subtract up and down and then take its average. So now the definition of VPD. We are going to call VPD as up minus down. So if I choose up minus down, you can quickly see that for positive phase errors, what will be positive? If I choose up minus down, for positive phase errors, what will happen? You'll get a negative value and vice versa, which is okay. It's only a matter of definition of KDL, right? So can you calculate what is the average value of VPD for case 1 and case 2? So I'm interested in VPD average. This is up minus down average. What is the average of up? So that is delta T into VDD divided by T naught. Minus what is the average of down? So that is simply T naught by 2 into VDD by T naught, which becomes VDD by 2. Right? But this is something you should be able to look at the figure and then tell also, right? For half the period, it is at VDD. For other half of the period, it is at 0. So the average will be VDD by 2. So let me take VDD by 2 outside. So this is minus 1. Can you tell me the first term in terms of phase error? So delta T by T naught is phase error by 2 pi. Now you have taken the 2 outside. Therefore, this is phase error by pi. Okay. What about this case? Quickly tell me the expression for this.
1 minus
what is the fraction? VDD by 2. 1 minus phase error by pi. Is this right? Okay, this is wrong.
Yes, relatively negative, right?
So we have assumed that the into is now leading in one, which means the phase error is a negative value, right? But in the calculation, we have already taken that into account. When we plotted these waveforms, we have already taken that into account. So you should put a, just to be safe, I'll put this. Okay. So how does the plot look like? VPD average versus phase error. You have the expression. Can you plot it from minus 2 pi to plus 2 pi? So you can sketch this as a homework. So plot the VPD average versus phase error. From minus 2 pi to plus 2 pi. And identify the monotonic range. We can wrap the class here. Thank you.